I would like to give a talk about learning good abstractions. But first, why do we need them in the first place? Abstractions allow us to consider only the important details of the problem. For example, here you wanted to reach your friend's house. You're using a state-of-the-art reinforcement learning agent, which does not know that go uphill probably means just choosing the correct street. It goes over all possible options to optimize for your reward, and you end up doing something that was not in your best interest. Hi, my name is Sergey, and I'm doing a semester project at EPFL. I would like to tell you about an interesting subproblem in reinforcement learning, learning abstract representations. We will define this problem formally and then analyze it theoretically to develop good solutions. Finally, we run simple experiments to show the feasibility of our proposed approach. So imagine you want to train a fancy reinforcement learning agent, such as PPO, on an Atari game such as Montezuma Revenge, and it fails. Why? What can be a reason? There are multitudes of things that can go wrong, from wrong hyperparameters to bugs, adversarial policies, non-convexity, bad reward choices, peculiarities of neural networks, too complex environments, wrong optimizers, catastrophic forgetting, and many others. The current solution is to have a dedicated human who would spend days of time to dig into the problem using latest state-of-the-art tinkering techniques. The problem would become even worse if we want to deploy an RL agent into a production system. What if it fails there? How can we possibly prevent a disaster? Or at least, how can we learn from a failure? It seems it would help us a lot if we had a common language with the agent, and it could tell us more about what the problem is. Abstract reasoning is one of the great methods that humans use to solve complex problems. The basic idea is to only think about what's important and ignore the rest. This way we have less things to try when we try to figure out a solution. In this project, we add abstract reasoning to our RL agent. Now, consider an Atari game. There is some simple logic to it. You can think of it as a very old code which runs on the cartridge using its 128 bytes of RAM. At each iteration, it only executes a very simple instruction, changing only a few bits in the memory. The observation is much more complex than that. It is an image which can change drastically between time steps, and some parts of it are completely irrelevant to the game. If we just train a model-free agent, we get suboptimal performance because exploration is unstructured and the agent overfits to extra details of the image. And if we fit a model to predict next observations, the model would be quite complex. Another approach is to learn latent dynamics. First transform the observation and then learn a model in that new space. This would help, especially if we can understand what the components of that new representation mean and how does the model work. So in this project, we introduce a regularizer for a model in RL, which forces the model to be sparse. It only contains a few non-zero components. This forces the representation to be interpretable. We show that the model as a graph to show which components affects each other. For example, you can see this graph is simple because it has only few edges. A fully connected graph does not tell us anything about the environment. We already know that every action can affect any state component prior to training or knowledge about the environment. Now, a reasonable representation for Montezuma Revenge would be to consider the current room we are in and connect it to a state indicating which key we need to collect. So, to sum up, good learned abstractions can lead to better understanding and solving more complex environments in an efficient way. We will be robust to non-important changes in the images, and thus we will be robust to modifications in the environment. And we formulate this problem in the following way. We want to learn good transformations from observations to features, such as the feature environment model is simple. By simplicity, we mean sparsity. We propose the following architecture. The model-free agent is additionally equipped with a learned sparse model. The decoder learns the map, transforming observations to features, and the model forces the decoder to converge to a representation where the model is sparse. The model gives a curiosity reward to the agent, so that the model does not overfit to only seen data. Specifically, since this is the first time this particular formulation is considered, we consider the full linear case. In addition, we will only consider one-time step dependencies. We consider a simple environment game engine where the next state is a linear transformation of the previous state and the action vector. Additionally, the observation is computed as a linear transformation of the state. Now, if the state had simple dynamics, such as Atari RAM representation, the observation model will not be simple. The agent is trained in a standard way using any RL algorithm, with an addition that the curiosity reward is added to prevent overfitting. The curiosity reward shows how much the model can explain the new data. The sparse model learner is the component that we introduced. It learns a model M on learned features, which are just linear transformation of the observation. Additionally, the model is regularized to be sparse and thus simple. We consider a very simple linear environment where the goal is to stay in the diagonal of the state space. Each action increments the corresponding component, and the reward is given if we move closer to the diagonal. This is the formal definition of the environment. As we see, the environment transition matrix A is sparse. It has only 4 components out of 8, and the optimal strategy is to always increment the lowest component. Now, we want to complexify the observation dynamics, like in Atari, where a RAM state is rendered as a high-dimensional image. To do so, we just do a fixed throughout the training linear mapping, which makes the observation dynamics hard to interpret. Now, how do we solve the problem of learned sparse models? First, we need to understand which losses to choose. We would like our model to feed the data to be sparse and the decoder to be non-degenerate. There is always a solution for the decoder to output 0, and then the model perfectly predicts the next time step. However, this decoder is degenerate. It's like closing your eyes and being happy that we can predict what happens next. There are many ways to formulate the fit, degeneracy, and sparsity conditions. Once we have the losses, there are many schemes to optimize for these losses. Specifically, we consider 2 methods. In method 1, we first estimate a matrix of observation transition dynamics. This matrix is not sparse. Next, we do some linear algebra to find the basis where the matrix becomes most sparse. In the second method, we jointly learn the dynamics and the sparse model, having 3 losses for the problem. We can see that when considered as a function of only one variable, these losses are often convex. However, if considered as a function of many variables, some losses are non-convex. We established that first, the problem of finding a most sparse environment model is NP-hard, even in our simple linear case. This is because we can reduce our problem to sparse dictionary learning, another NP-hard problem. The whole complexity of the problem lies in optimizing for the loss. Specifically, if we had a perfect optimizer that always returns a global minimum, the problem would be easily solvable. Our experiments agree with our theoretical results. Specifically, the success ratio of our algorithm is never 100%. Some random initializations lead to bad valleys, which local search cannot escape. However, the loss landscape seems better with higher dimensions. This is a result for dimension of 5, for states, observations, and features. On the left figure, we see that in 50% of the cases, over decoder initializations, we converge to the correct number of non-zero components in M. On this chart on the right, you see the visualization of the learned model M. It is sparse with a minimal number of components to stay non-degenerate. During debugging the training procedure, the following analogy was helpful. We consider the fit and sparsity loss as a student who tries to develop her own understanding, and the non-degeneracy loss as a teacher. If the teacher loss is too strong, the representations are forced to stay in one particular valley, with no chance of escape. The student learns a non-degenerate representation, but the model is not the most simple one. If the student loss is too strong, the model would be sparse at the end, but the representation might become degenerate. Here is one of the successful trials. On the left, we see a histogram of weights of the learned models. It is clear that there are 2 clusters, weights close to 0 and weights close to a constant. If we threshold based on clustering techniques, we get the following very simple graph. Here, each feature determines the value of this feature at the next iteration, and one action corresponds to one feature. This is exactly what we wanted. However, the row observation model graph is quite complex to understand. This is a sparse model learner loss landscape in the descent curve PCA space. You see that it is highly non-convex and that local minima have different values. This brings me to the end of my presentation. We have considered the problem of learning abstractions in DeepRL. We show that this problem is NP-hard and non-convex, even in the simple linear case, with no obvious way to improve the situation. However, we show that the success ratio is non-zero and we can in principle learn better abstractions. Next, we would like to switch to more complex environments such as grid worlds and Atari. We want to reuse the insights that we gain from our simple linear Markov case and apply them to more complex settings. This picture shows that even in human abstractions, the loss can be non-convex. There are 2 ways to look at the figure. Either the deer is crossing the road or the road is crossing the forest. And before knowing that there exists another representation, we can't know that it is there. This might be because we are in different valleys which local search cannot escape. Thank you for your time. Please ask me questions if you have them.